Okay, so gravimetric analysis is just a laboratory procedure where we talk about two substances, usually in an aqueous solution, and you mix them together and you can produce a precipitate or a solid, and then you try to isolate the solid by usually filtration, dumping out, any sort of excess analyte or whatnot. That is left in the container, and then the precipitate or the solid sticks to the filter paper, and then we wash it to get rid of any sort of excess ions or impurities, and then we would let it dry overnight, or often we have ovens that we can dry them into to help them dry faster, but you definitely want them to be dry, otherwise you won't have the true mass of your precipitate. You'll have a wet precipitate, which would include water and such. So again, this gravimetric analysis is just this fancy word for how we can, in a laboratory setting, isolate certain precipitates. Okay. So this first question we're going to do is a sample of copper 2 sulfate pentahydrate. Ooh, so you should know how to write this guy's formula by now. Please try to write it. Copper 2 sulfate pentahydrate. So copper 2 sulfate, so that is CuSO4, penta, 5 hydrate, 5 waters, okay? And I give you a mass of the copper 2 sulfate pentahydrate and how much water it is dissolved in. So in this first sentence, what are they doing? They're preparing a solution. They're taking this solution, or taking this solid, and making a solution with it. So in the first sentence, what can we find out about the copper 2 sulfate pentahydrate? If we know the mass of the solute and the volume of the solution, what can we find out? Hello? I'll wait. Yes, molarity. Thank you, Andy. So you can find out molarity. You have grams. You can turn grams into moles. So it's 8.512 grams of the copper 2 sulfate pentahydrate. And you can turn grams into moles using molar mass. Now, you guys have been relying on me a lot for molar mass, so I'm not going to do it for you this time. I want you to find this guy's molar mass. So you will take a copper plus sulfur plus 4 oxygens plus 5 waters and add it to the molar mass. And now I'm going to wait until someone has it. Okay, so we've got the molar mass, so our moles end up being, and I'm apologizing to my second period right now, I think this number was incorrect on my slide, so I think it messed up the problem in terms of the final outcome. So look back over this. So moles per liter. So 500 milliliters is 0.5 liters. That's going to give me my molarity of my copper 2 sulfate pentahydrate solution. So the molarity is 0.06817 molar. Okay, so in essence, I'm going to erase this in a minute. They take copper 2 sulfate pentahydrate, specifically 8.512 grams, and they dissolve it in enough solution to make 500 milliliters. Okay, and now you have this 0.06817 molar solution, 817 molar solution of copper 2 sulfate pentahydrate. Well, now what they're going to do is they're going to take a small portion of this solution that they just made. So a 25 milliliter sample. So 25 milliliters of this solution. 25 milliliters of 0.0618 molar. They're going to put it in there and they're going to react it with something that has iodide ions. Okay, maybe it's potassium iodide, maybe it's sodium iodide, maybe it's lithium iodide. It's some sort of iodide. The reason that is is because copper ions in the presence of iodide ions produces a precipitate. Okay, so that is what they're doing. But what they want in this question is not like, oh, how much precipitate are you going to make? They want to know what ratio do the copper and the iodide ions react. Now, because you don't know who the iodide source is, like you don't know if it's potassium iodide, you don't know if it's calcium iodide, you don't know the mole to mole ratio. So we're actually solving for something that we normally know. We do know the molarity and the volume of copper 2 sulfate we're using. So we can know the moles that we're using. So, oops. Molarity times volume, 25 milliliters, 0.025 liters, gives you moles of the copper 2 sulfate pentahydrate. 0.06817 times 0.025, so 0.0017-ish, okay, moles of copper 2 sulfate, which in essence is moles of copper 2 plus ions. Why? For every 1 copper 2 sulfate, there is 1 copper ion. So what's crazy is they're asking for the mole to mole ratio, which is this guy, moles of copper ion reacting to moles of iodide ion. Now, we don't know this. This is our like unknown. Okay, we don't know it, but we do know the outcome because we know the molarity and the volume of iodide that they used. So we do know how many moles of iodide were needed to react. So we have this number over here. I shouldn't put X. We know this number. This is an actual number. So you're used to calculating this number by using mole ratios. Now you know this number and you're going to work backwards to find the mole ratios. So I'm going to clear this out so you can kind of see. We know we have 0.0017 moles of copper 2 plus ions. And we don't know this. And we don't know this. But we do know how many moles of iodide ions there are because we know its molarity and we know its volume. 0.1702 moles per liter of iodide times 0.02 liters is 0.003404 moles of iodide ions. So how do I get this ratio? Well, I divide both sides by this guy. This is like my X, you can call it. 0.0017. 0.0017, and you get a 2-to-1 ratio. So for every 2 moles of iodide, there's 1 mole of copper ion that reacts. 2 of the iodide and 1 of the copper. Now this should make sense. Copper is +2, right? It's copper 2. Iodide is -1. How many iodides do I need? I need 2 iodides for every copper 2 plus ion. So this is what makes sense. 2-to-1 ratio. That is the molar ratio. Every 2 moles of iodide ions, there's 1 mole of copper ions. Okay. Do you have any questions before we move on? All right. So gravimetric analysis of precipitation reactions. So a solid of unknown composition has some chlorides. So maybe it's sodium chloride, maybe it's potassium chloride, maybe it's lithium chloride, maybe it's calcium chloride. Who knows what it is? Something with chloride ions. They take it and they dissolve it in water. So the reason they do that, so let's pretend, let's see. They take this salt, some sort of salt, something chloride, and they take it and they put it in here and they dissolve it in water. And the reason they do that is because they want to get the chloride ions to float around. In the solid, there's not chloride ions floating around. It's either NaCl or KCl or something with Cl, but when you introduce the water, you can get the chloride in ion form instead of in the solid form. Okay? So the solution has a large amount of silver ions added to it until no more precipitate can be formed. Okay, let's see. I think I made an extra page. No, I didn't. Shoot. So now you have this container that has chloride ions floating around in it and something else. It's probably like sodium ions, potassium ions. It's not going to matter because they're going to throw something in here that has silver ions in it. Maybe let's pretend, let's say it's silver nitrate, but some source of silver ions. Well, what happens when silver ions see the chloride ions? Well, they hook up. Chloride ions are not soluble, meaning they cannot float around in here as ions when silver is in there. They produce a precipitate called silver chloride. It's on your solubility rules. Chloride ions are soluble, but not with silver. So what they've done is they've yanked the chloride ions out of solution by putting them with silver. And now you have silver chloride sitting on the bottom, and then some sort of other ions. Let's pretend just for fun. Let's say it was silver nitrate. There's my silver ions, and it was sodium chloride. You'd make sodium nitrate and silver chloride. For example, this is just a sample of what it could be. Here's your precipitate, and then you would have, for example, sodium ions, which are soluble, and nitrate ions just floating around up top. Okay? So it says identify the precipitate formed. Well, silver chloride is the precipitate formed. Okay, now I want to know the moles of the precipitate. Well, if you know grams of the precipitate, you can easily turn that into moles. 0.287 grams of silver chloride. Turn grams into moles using the periodic table. I'll wait for a molar mass for silver chloride. 1 silver plus 1 chlorine. 143.32, I think. So the moles for part B is 0.287 divided by 143.32, 0.00200 moles of silver chloride for part B. Now AgCl. They want to know the moles of chloride ions present. Well, this is easy. To get the moles of chloride ions present, you just break the compound down into ions. 1 mole of silver chloride has 1 mole of chloride ions in it. There's 1 chloride. So this is also 0.00200 moles of chloride ion. Okay, I gotta erase this, otherwise I'm gonna run out of room again. So now part D says calculate the mass. So I have to turn moles into grams. This isn't a trick question. You should be able to turn moles into grams. 0.00200 moles of chloride ion. 1 mole of chloride ion is 35.45 grams. The charge does not affect the molar mass. You go find chlorine on your periodic table, and that's its mass. Remember that we pretend that electrons, or we don't pretend, but we generally pretend that electrons that have very, very little or low mass. It's negligible compared to like our protons and our neutrons. So the molar mass on the periodic table, this -1 doesn't affect it. Go find chlorine, it's 35.45. So for that number, you get so the mass percentage of chloride ions is the mass is 0.0710 grams with sig figs. Okay. So they want to know the mass percent of chloride ions in the original sample. Well, if this is the mass of chloride ions, and this is how much had the original sample in it, so this wasn't just chloride ions, this was something and chloride ions. Maybe it was sodium and chloride, maybe it was lithium and chloride, maybe it was potassium and chloride. The whole thing is we don't know. So if I take my grams of my chloride and I divide by my total mass, and then I multiply by 100, I can turn it into a percent of chloride ions. And that is going to be, sorry for running out of room, it is 39.0% chloride ions by mass, which means the rest of the mass belongs to whoever chloride was hooked up with. Maybe it was sodium, maybe it was potassium, maybe it was lithium. Who knows who it was hooked up with? Okay, so the final question says, what effect on the calculated value in part E, so that's this 39%, what would the effect on the value be if the precipitate were partially dried, meaning the precipitate was still wet? Well, if the precipitate is still wet, this number right here, the precipitate, is going to be higher or lower artificially? Higher or lower? Heavier or lighter if it's still wet? No one knows?
Heavier.
Okay, heavier. So this number is going to be bigger. Well, if the precipitate, if this number is artificially bigger, then the number of chloride ions are artificially going to be bigger. You're going to assume there's more chloride ions. And if there's more chloride ions, your percent of chloride would go up because you're assuming the water to be some of it silver ions and some of it chloride ions. And it's not. You just didn't finish drying it. So you'd have an artificially high amount of percent of chloride ions because you haven't gotten fully rid of the water and you're assuming them to be chloride ions and not water. So the number would be too high artificially. You'd end up with a bigger number, like maybe 50% or 60%. But it really isn't that of chloride because some of that is water if it's still wet or not dry. Any questions about F? Okay. I tried to fix this slide because it's very small and kids were having a pretty hard time reading it. So hopefully it'll help just at least a little bit. So this FRQ from 2011, the first part is stuff that we've already learned last week. The last part down here with the table is what we're doing right now in this class today. Okay, so I'm going to see if I switch, if this helps. It says a student is assigned the task of determining the mass percent of silver in an alloy of copper and silver by dissolving the sample in nitric acid and then precipitating the silver as silver chloride. So let's talk about this. They're taking a container, okay, so an alloy that has silver and copper in it. So it's got like some copper. And an alloy is a metal, okay? It's a mixture of metals. Oops, I did not want red. And it's got some silver in it, okay? And it's this just chunk of solid that if you dropped this alloy that has copper and silver in it in water, it would literally just sink to the bottom and do nothing. So what they've done is they've put it in a flask with nitric acid, because nitric acid will dissolve the solid. Okay, the water won't, but the nitric acid will. So when this alloy dissolves, it allows it to break apart into its respective ions. So now in here, we're going to have copper ions and silver ions floating around. So they add the nitric acid to it. Then what they do is they take and they dump excess sodium chloride in here. Now, it's not really the sodium that matters. Remember, sodium ion in solution will float around as Na+, and Na+ is always soluble. The problem is that the chloride ion will hook up with the silver. We know silver chloride is not soluble. So what happens is you, in the end, I'll draw a new beaker, you will get some silver chloride sitting down here at the bottom. And then floating around in solution are your sodium ions, your copper ions from the alloy. Copper chloride is soluble, so the chloride doesn't affect the copper either. Sodium ions, copper ions, and then all of the silver chloride precipitates out. Okay? Question so far. So, it says the student is provided with a stock solution, so super duper concentrated 16 molar nitric acid. They give you a bunch of lab equipment and then some safety equipment, and then they ask you for part 1 to calculate the volume in milliliters that the student should use for preparing 50 milliliters of 6 molar. So they give you 16 molar and you need to turn it into 6 molar. What type of problem is this mathematically? Taking something that's 16 molar and it's dropping down to 6 molar. This is a dilution problem. What is the equation for dilution? M1V1, M2V2. So M1 is 16 molar. V1 is, I don't know. The new molarity is 6 molar. And the new volume is 50 milliliters. So you take both sides, you divide by 15. Please give me the answer in milliliters to the correct number of significant figures. It should be 20. It's 18.75. But this is a 1 sig fig number, so it should be 20 milliliters. Question so far? Okay, list the steps of how to prepare this solution using only the materials provided. So I'm going to go back here because this is going to give me some more room. So list how you would prepare the solution. So the first thing you're always going to do is put on safety equipment, whatever they give you. So step number 1, put on goggles. What else did they give you? Gloves and gloves. Sometimes they'll give you an apron, put that on too, okay? Step number 2, measure out. 20 milliliters of 16 molar nitric acid with what? What are you going to measure that out with? What tool? Anybody? What's the best tool to use? Graduated cylinder. You don't ever measure volume in beakers. Now, this is where you have to be very careful. Can you just dump water on top of that? On top of 16 molar nitric acid? No way. So in the other 100 milliliter graduated cylinder, add some distilled water. You can be specific right here. If you're going to have 20 milliliters of the nitric acid, the rest of it's going to be water. If my final volume is 50, that technically means 30 milliliters of it is going to be water because 30 plus 20 is 50. So you could be specific here. I'm not. In the other 100 milliliter graduated cylinder, add some distilled water. This is the most important step. Add acid into the water and stir with the stirring rod. And then fill up to 50 milliliters with distilled water. Now, in step 3, if you were specific right here and you say add 30 milliliters to the 100 of water to the 100 graduated cylinder, and then you add the 20 of the acid, the step number 5 would not be necessary. If you're very specific in step 3 of exactly how much water is going to be in there, you technically don't need step 5. So again, this can vary slightly. Always put safety equipment on. Acid always goes into water, and we always measure volumes in really good containers like graduated cylinders. Any questions? Okay. So explain why it is not necessary to use a volumetric flask. So remember, volumetric flasks are another container that we often make solutions in to perform the dilution. Well, we have graduated cylinders that read to the 1 milliliter mark. So they still read to a good number of significant figures. So it's not necessary to actually use a volumetric flask. Our graduated cylinders have good markings on them. They're good enough, okay? All right, number 4, and almost everybody has gotten this wrong today. During the preparation of the solution, the student spills the really, really concentrated nitric acid on the bench top. And the student finds 3 bottles, a bottle of water, distilled water, a bottle of sodium bicarbonate, and a bottle of sodium chloride. Which liquid is best to clean up the spill on the lab table? Anybody know? What do we clean up acid spills with?
Wasn't it like vinegar or any type of, not vinegar, sorry, any type of base?
Any type of base, which is who in this problem? Sodium bicarbonate, because it's baking soda and it will neutralize the acid. If you were to have spilled on yourself, you would use water. But when it spills on the table or the ground, we will neutralize it with some baking soda or some sodium bicarbonate because it neutralizes the acid. Any questions for number 4? Part 4, I guess I should say. All right, so the student takes a certain volume. I'm going to go here. A certain volume and molarity, and they dump it onto the sample, the alloy. So this is the copper silver chunk, okay? The copper silver chunk dissolves into copper ion and silver ion, and then they throw a bunch of sodium chloride ion in there. So you got copper ion floating around in here once it's dissolved in the really strong acid, and silver ion floating around in here. And then they dump some sodium chloride in here, which is sodium ion and chloride ion. And the chloride sees the silver and it precipitates out of solution to make silver chloride. Okay. Part B asks you to calculate the number of moles of silver chloride precipitate collected. So this is the sample, this is the alloy, this is its solid before it got dissolved. This is the dry crucible, so this is the container. This is container with the precipitate, which is silver chloride, and they did it 3 times. They weighed it 3 times. How did they know they finished? Well, look at this is 29.35. And then it dropped to 29.25, and then between the second and third weighing, it stayed the same. So they knew that they were finished. So what do I know about the precipitate? Well, I know its mass. How do I know its mass? This is the precipitate in the container, and this is the container. So if I can subtract them, I'll get the mass of the precipitate. So 29.2599 grams of silver chloride. That's the precipitate. Minus 28, the container, 0.7210 grams of the container. We don't want the container. This is the precipitate and container. And you get what? 29 point, 0.2599. You could also use 0.2598. It doesn't matter. 28.7210. This is 0.5389 grams of silver chloride, and they didn't ask for grams, they asked for moles, but you should be able to look up silver chloride on the periodic table. It's 143.32. So this is 0.003760 moles of silver chloride. Questions on how I got that using lab data? Okay, so the next part asks me, okay, what percent by mass of the alloy, which this is the mass of the alloy before we dissolved it, what percent of it's silver? Well, if I know the moles of silver chloride, I know the moles of silver. Why? 0.003760 moles of silver chloride. Every 1 mole of silver chloride has 1 mole of silver in it. And I'm sorry I have to do this way. 1 mole of silver is 107.87 grams. 107.87 grams. So for every 1 silver chloride, there's 1 silver ion. So the mass of silver in the compound is 0.4056 grams. Well, the total mass of the compound, so this guy is the copper and the silver, right? That sample. So the total mass of the alloy is 0.6489. You take the mass of the silver, divide it by total mass, and then multiply by 100 to get percent. .51 or 0.50% of the alloy is silver by mass. Any questions?